Now, let's do another example or another exam question paper. In the diagram, COD is a diameter of the circle with center O. EA is a tangent to the circle at F, is a tangent to the circle at F. OA is perpendicular to CE. OA is perpendicular to CE, as you can see there, perpendicular to CE, as you can see there. Diameter COD produced meet the tangent at E. Diameter COD produced intersects the tangent to the circle at E. OB produced intersect the tangents to the circle at A. OB produced intersect the tangent at A. Now CF intersects OB. CF intersects OB at T, as we can see there. CB, BD, OF, CB, BD, OF, and DF are drawn. We are told to prove with reasons that TODF is a cyclic quadrilateral. Now, we need to first eliminate all the theorems which are not in the problem. Now, we do have chords, we were never told about any cyclic quad here. Therefore, we'll just say cyclic quads are not there. Now, tangents, there is a tangent in this problem. Now, let's eliminate chord theorems. Is there line from the center to the midpoint of the chord? No, there's no line from the center to the midpoint of any chord here. Is there angle at the center is 2 times angle at the circumference? No. Is there angle subtended by diameter? Yes, there is an angle subtended by diameter. You can see this angle is subtended by diameter, and even this angle here is subtended by a diameter there. Therefore, theorem number 3 is there in this problem. Are there angles on the same segment? Yes. Are there angles on the same segment? Let's see. Angles on the same segment. There are no angles. There are angles on the same segment. Let's see. This and that, they are the only angles on the same segment here. Because this and that, we can't say they are on the same segment because they're just subtended by the radius. So we can't say this angle is equals to that angle there. We can't. So theorem number 4 is there by this and that. It is there. Theorem number 4. But it is there in a form of theorem number 3. Therefore, I can just say T4. It's there. Theorem number 4. Now, theorem number 5 and 6, we said they're out because they didn't talk about cyclic quads here. Now, theorem number 7, which a radius perpendicular to the tangent at the point of contact. Therefore, yes, it is there. There's your radius going to be perpendicular to the tangent. Therefore, T7. No tangents from the same point. You only have one tangent. If there were 2 tangents, then we're going to talk about theorem number 8. Theorem number 9, we do have theorem number 9 here, because there's an angle which is made by the chord and the tangent. Therefore, it's going to be equals to an angle in the alternate segment. Therefore, we have T9 there. Therefore, we might use all these theorems we know from part 2, 3, and from part 2 and 3. So we can use these theorems, or we can use some of these theorems. Now, we are told to prove with reasons that TODF is a cyclic quadrilateral. Now, for us to prove that TODF is a cyclic quadrilateral, We know we can use exterior angle of a cyclic quad. We can also use opposite angles of a cyclic quad. From what I can see here, already I am given 90 degrees there, which is an exterior angle of this cyclic quad. Therefore, I think there is where I can start. Now, we start A. Angle O1 is equals to 90 degrees. Reason given. We are given that. That's O1. Now, F3 plus F2, this angle here is 90. Because this angle, it is subtended by the diameter, theorem number 3. Therefore, this angle is subtended by the diameter. It means that this is 90 degrees. Therefore, we know that angle F3 plus angle F2 is equals to 90 degrees. Reason angle at semicircle or angle subtended by a diameter or by diameter CD. Now, therefore, angle O1 is equals to angle F3 plus angle F2. Both equals to 90 degrees. Therefore, TODF is a cyclic quadrilateral. Why is it a cyclic quadrilateral? It is because reason exterior angle of cyclic quad, I can shorten it like this, cyclic quad is equals to the opposite interior angle. That is why TODF is a cyclic quadrilateral. Now they say to us, B, prove that angle D3 is equal to angle T1. Prove that this angle is equals to angle T1, this angle there. We must prove that this angle, I'm going to use red, we're going to prove that this angle is equals to this angle there. We're going to prove that the two angles are equal. Now, I need to remove here for me to write B. B. B, we are proving that this angle is equals to that angle. But now, we can see that this angle is an exterior angle of this cyclic quad. Already we have proved that this is a cyclic quad. And we know that there's an imaginary circle there. It's not cyclic for this circle. We can have an imaginary circle around there because we have proved that it is cyclic. Now, this is an exterior angle of a cyclic quad, which is equal to the opposite interior angle, which is T3. B. Angle D3 is equals to angle T3. Reason, exterior angle of cyclic quad is equals to opposite interior angle. Now, since this angle is equals to that angle, and angle T3 is equals to angle T1, risen, vertically opposite angles. Therefore, angle D3 is equals to angle T1, both equals to angle, both equals to T3, angle T3. They both equals to angle T3. Therefore, we have proved B, that angle D3 is equals to angle T1. Now C, we are told to prove that triangle TFO, this triangle TFO is similar to triangle DFE, is similar to triangle DFE. So we need to prove that this triangle is similar to this triangle there. Now, I remove B because I've already done it. C. Now, for us to prove that the two are similar, already this angle here, we've seen from B that this angle in this triangle is equals to this angle and this triangle. We start there. In triangle TFO and triangle DFE, since we can talk about angles, then it means that you are going to prove this using equiangular triangles, where all corresponding angles are equal. Therefore, the first angles which are which are equal is angle D3. Angle D3 is equals to angle T3. Reason? We have proved it. Proved. I think I'm going to say proved. Or we could have said exterior angle of a cyclic quad is equals to the opposite interior angle. But no need for us to say that. We have proved it on B. Now, this is the angle which is equals to this angle there in this triangle and this triangle. Now, for us to get another angle which is in this triangle, which is equals to an angle in this triangle, we can look at this one here, which is F4. F4, since it is made by the tangent and the chord, so it's going to be equals to this angle there. Because this angle is subtended by this chord, which makes an angle with the tangent. Therefore, we say that angle F4 is equals to angle C2. Reason? Tongue. Chord. Theorem. Which is our theorem number 9 there. Now, this angle is equals to that angle, meaning that this angle here obviously is going to be equals to this angle there, which is F2. Angle C2 is equals to angle F2. Reason? There's a radius, there's a radius. Therefore, these are base angles. Sorry, I must do that with blue. These are base angles of an isosceles triangle. Therefore, triangle OFC. OFC is isosceles triangle. Why is it isosceles triangle? Because I have OC equals to OF. OC equals to OF. Therefore, we know that this triangle, this angle, is going to be equals to this angle there. This angle, therefore, F4 is equals to angle F2. This angle in this triangle is equals to this angle in this triangle. Already we've got two angles which are equal. This is equals to that. We know, we've just said it, that this is equals to that. And this triangle, this is equals to that. And this triangle, obviously this angle there will be equals to that angle there, which is the third angle of a triangle. Therefore, angle E, I can conclude from here that these two are similar because I've got two angles on one triangle which are equals to two angles on another triangle. This angle and this angle, this angle and this angle. Two angles on one triangle, two angles on one triangle equals to two angles on another triangle. Therefore, these two triangles are similar, which they are equiangular. Or we can continue with it where we say angle E is equals to angle O2. We give a reason that third angle of a triangle. Therefore, triangle TFO is similar to triangle DFE. That's our C. We've proved it. D, they say if B2 is equals to angle E, prove that DB, prove that DB is parallel to EA. If we are told that this angle is equals to this angle there, prove that this is parallel to that. I'm going to remove C because I've already wrote C. Now for us to prove that these two sides are parallel, if I'm given that to be equals to that. We know that this angle there, which is angle angle B2, this angle is equals to this angle there. Angle B2 is equals to angle D1. Reason, triangle ODB is isosceles triangle. Why is it isos? OB is equals to OD. OB is equals to OD. Therefore, this angle is equals to that angle there. Therefore, angle E is equals to angle D1. Therefore, angle E is equals to angle D1. Why is that? It is because we were told that angle B2 is equals to angle E. Since angle B2 is equals to angle E and angle B2 is equals to angle D1, Therefore, it means that angle E is equals to angle D1. Therefore, DB is parallel to EA. Why is that? It is because corresponding angles are equal. This angle is equals to this angle there. Corresponding angles are equal. Corresponding angles are equal. Corresponding angles are equal. That is why this is equals to that, since this is equals to that. That is why BD is parallel to EA. Now, E. We need to prove that DO is equals to TO times FE over AB. We can use the parallel line which is drawn to one side of a triangle which divides the other two sides in the same ratio. But since we have DO here, AB is there, it's fine. FE. Now, FE is different from that which is parallel to that. So it means that we are going to use theorem 1 where this line is parallel to that and divides the other sides in the same ratio. We are also going to use what we have proved from C, that this triangle here is similar to this triangle here. Then we're going to set up our ratio. Then we are going to be able to prove that here. What makes me to think that we are going to use the theorem, it is because I can see that FE is in this triangle. Yes, your OD or your DO and your TO, you can see your TO here. It's in this triangle here. Also, it means that I'm going to use this triangle and this triangle to set up ratio. Then use theorem number 1 to set up ratio again. Then I'm going to have a side which is going to be common to the two ratios. Then solve for this. Let's see what I am saying exactly. Let me remove here. Now, we have just proved that this is parallel to that, E. Since OD over ED. OD over ED is equals to OB. We know since these two are parallel, therefore these two sides are divided in the same proportion or in the same ratio. Therefore this over that, since these two sides are parallel, is equals to this over that. So OD over ED is equals to OB over AB. Why is that? It is because line segment drawn parallel one side of triangle. Line drawn parallel one side of a triangle, that is why we have that. Now, we can see that we want EF and AB. Where's our AB? AB. Already our AB is there. Now, I can use this and this triangle, where we can see that EF which is opposite this angle there. Therefore, we can have EF. EF is opposite this angle and this triangle over OF, which is opposite this angle and this triangle, is equals to, we've just found our EF or FE. Now we need TO. Therefore, TO is opposite this. So it means that since we have started in this triangle where we said EF over OF is equals to, we still need to start in this triangle here, which is equals to DE. We start in this triangle here, which is DE over, obviously it is opposite, which is TO, over TO. Why is this? Because triangle TFO is similar to triangle DFE. This is why. Now, I can see that there's DE here, or ED, there's DE or ED here. I can make here ED the subject of the formula. I make it. This times this is going to be ED dot OB is equals to AB dot OD. So I want ED. Obviously, I'm going to divide by OB, divide by OB. Therefore, ED is equals to AB dot OD divided by OB. From here, I have him. Now, from him, I can make DE to be subject of the formula. There, I cross multiply. DE dot OF is equals to TO dot EF. I want DE. Obviously, I'm going to divide by OF. Therefore, DE is equals to TO dot EF over OF. Now, D is equals to that. Therefore, from him, we get that here. Now, I just want to continue with this here, where we're going to say these two are equal, since they are both equals to DE or ED. Therefore, AB dot OD over OB is equals to, obviously is equals to TO dot EF over OF. They both, this is equals to ED, this is equals to ED. Therefore, this is equals to that. Now, we can put OD here. OB is the same as OD. So I can put OD here. This is equals to that. It's a radius. OB equals to OD. Therefore, it means that AB dot OD over OD. This D, OD will cancel that one there. OF, it's still OD. OF, it still equals to OD because it is the radius. It is the radius. Therefore, this radius is equals to that, is also equals to that. Where I see OF and OB, I put OD. Therefore, TO dot EF over DO. Now, obviously, this we'll multiply that. We are going to have AB dot DO is equals to TO dot EF. Because this cancels, here we're left with AB over 1. This multiplied by that, it becomes this. This multiplied by 1, because there's a 1 here, it becomes that. I want DO, I divide by AB, divide by AB. Obviously, this cancels with that. DO is equals to TO dot EF over AB, which is what we were looking for number E. So for number E, you should be wise. You should look at your sides. DO, it's there. AB is there. O. So it means that TF, EF is in this one, and TO is in this one. Oh, so it means that they've asked us to prove this, then we have proved that the two are parallel. Therefore, it means that we're going to use theorem number 1, where this side is drawn parallel to one side of a triangle, where it divides the other two sides in the same ratio. But since we also need OT and EF, it means that we should use this in C, where we have this triangle, to be similar to this triangle, and look at our sides that we are looking for so that we can set up our ratio and equate the two and make, since here I've got ED and here I've got ED or DE, then I can make ED the subject of the formula there and make it subject of the formula for also this one. Then I equate the two, since they both equals to DE, I equate the two there. Therefore, OB is the same as OD. I put OD there. Therefore, this OD cancels with that. I'm left with AB over 1 there equals to OF is also equals to DO. Therefore, where I see OF, I put DO. Then, obviously, this is over 1. This multiplied by this, I get there. Then, this multiplied by 1 there, I get that. Now I want DO, I divide by AB on both sides. In mathematics, whatever that you do on the left, you must do on the right, and get your DO to be equals to TO dot EF over AB.